right, hello, and welcome to our final week of lecture. This is actually our penultimate lecture, which is a word that means second to last. So it has been a long journey. We're not quite at the end of the semester yet, but we're close. I'm going to continue our discussion of buffers. Today, conclude our discussion of buffers. We're going to be wrapping up chapter 9 and then cracking into chapter 10. We're not going to cover all of chapter 10. Chapter 10. Just there's a couple things that I'm going to touch on, and then I'll also, at the end, once I'm done lecturing in chapter 10, spell out exactly how it'll show up on the final. I'm not going to dump a ton of information on you for the chapter 10 stuff, because again, you're seeing it a week before the final. It's going to be very rudimentary, and it won't be too bad. All right. But first, before we get to radiation, we need to wrap up our acid-base discussion with a discussion of buffers. So we gave an example, or I gave an example, at the end of class last week, where I said you had a buffer of hydrofluoric acid and fluoride, right? And again, just refreshing our memories. A buffer is a solution that contains both a weak acid and its conjugate base, fluoride being the conjugate base of the weak acid, hydrofluoric acid. And I asked you to write a balanced chemical equation of what would happen when you add acid and when you add base to this buffered solution. Now, typically when you add acid, you're producing more hydronium ion and the pH is going to rise. But here, when you add acid, or I think I did HA. When you add acid to a buffered solution, the acid doesn't have a chance to react directly with water because turns out there is a base in solution, right? So when you add acid, it's going to react with the conjugate base of your buffered solution. And what it will produce is it's going to produce, well, let's see. Fluoride is the conjugate base, which means it is a proton acceptor. So it'll become HF plus the conjugate base of whatever acid you added, A minus. And as you can see, the important part about this is no hydronium is produced. It's made a little bit of hydrofluoric acid, but guess what? Hydrofluoric acid was already a part of this solution, so it really hasn't changed. It's produced a little more of it, but it hasn't really changed the composition of the buffer at all. When you add base to a buffered solution, so we'll use B minus as our representative base. The base doesn't get a chance to react directly with water either because we have an acid in solution, HF. And when this base reacts with HF, it's going to accept a proton, so it's going to become the conjugate acid HB. Oops. There we go. Plus fluoride. All right? And again, the important thing about this reaction, or the products of this reaction, is no hydroxide is produced. And F minus is already part of our buffered solution, so it doesn't change the composition of the solution all that much. So that is how a buffer resists changes to its pH, because it kind of has two things simultaneously going on. It's got F minus, it's got the conjugate base, which defends against acidic change. Then it's got the conjugate acid, which defends against acidic changes, basic changes and acidic changes. It resists both of these because it can kind of fight on both fronts. So that is how a buffer resists changes to its pH. All right, now the last thing we have to talk about is the pH of buffered solutions. All right, the pH of buffered solutions, which the way we determine the pH of a buffered solution is with something called, the Henderson-Hasselbalch equation. And it's Hasselbalch, the Henderson-Hasselbalch equation. When I was taking general chemistry, first year of college, straight out of high school, I had a friend who was taking the class with me, and he called it the David Hasselhoff equation. And I don't know if that helps it stick in your mind any better. It definitely helped me remember. Not that it helped me remember the equation, but it always was like, oh yeah, David Hasselhoff equation, which is the pH of a buffered solution. So this is explicitly only for buffers. The pH of a buffered solution is equal to the pKa plus the logarithm of the concentration of conjugate base divided by the concentration of weak acid. All right, and specifically, not just the concentration, but the molarity of each of these. Okay, I'm totally drawing a blank here. Hang on 1 second. I apologize. I just need to check. Oh, wait. Oh, well. There we go. Okay. So the pKa, again, this is, oops. Let me open a new slide. The pKa again is the negative logarithm of the acid ionization constant. So that's the equation for pKa and Ka. Is just the equilibrium constant for the reaction of the equilibrium of an acid reacting with water. The products here are hydronium and the conjugate base. All right, but the thing is, you're either given the pKa or you're given the Ka, and you plug it into this equation. So that really, the pKa, the take home is that's a number you look up. And then the both HA and A minus, this information is usually given in the problem. So this equation isn't The hardest to use, you just have to plug in all the respective values. So problems involving the Henderson-Hasselbalch equation go something like this. So let's do an example. What is the pH of a solution with a molarity of acetic acid? Acetic acid, that should be a 2, is equal to 0.500 molar, and the molarity of acetate, which is the conjugate base, is equal to 0.350 molar, and the pKa of acetic acid, acetic acid, is 4.75. All right, well, because we're dealing with a buffered solution, right, we have HA right here. This is HA, our weak acid. This is A minus, our conjugate base. The pH for the buffered solution is equal to the pKa plus the logarithm of the concentration of conjugate base divided by the concentration of weak acid. And so pKa is 4.75. And now we have to find the logarithm of our molarity of conjugate base, 0.350, over the molarity of weak acid, 0.500. All right, and one of the things you'll notice is molarity cancels. And so you're going to need a scientific calculator to perform this part. You go 0.35 divided by 0.5 is 0.7, and we have to take the log. If you're using a scientific calculator, the button that you're going to need to push is the one that says log base 10. So this is, our pH is equal to 4.75. The log of 0.35 divided by 0.5 is negative 0.155. This is one problem where you don't have to worry about sig figs because we're dealing with logarithms. They have different rules for sig figs, so don't even trip. So we got to add 4.75 to this. And so our pH of this buffered solution comes out to be 4.60. Is our pH. So it really is just an equation about plugging in your results. You got your two molarities, you got our pKa, you got to use a logarithm on your calculator, but that's about all there is to it. And this brings to a close chapter 9. Now we're ready to dive into chapter 10. There we go. All right, I've got to switch over my notes here. All right. So chapter 10 is the end. This is the very last bit for us, and this is a chapter dealing with radioactive decay. And radiation. So we're going to be getting a little bit into nuclear chemistry. This is kind of honestly more the realm of physics and physical chemistry more than it is chemistry proper. Typically, the people studying this field tend to be more physicists than they do chemists. But we're going to, this is an introduction. Again, we're not going to cover the whole chapter. We're going to kind of stick to the basics, the bare bones of what would be good to be exposed to. There. I said it. It's good to be exposed to a little radiation. All right, sorry. I couldn't resist the dad joke. So we're going to kind of get into it and focus on the chemistry behind radioactivity and radioactive decay. Look at a couple modes of radioactive decay, and then again, I'm going to close up the chapter, possibly today, with words are just flying out of my brain. Close. I'm going to tell you exactly what to expect from this chapter on the final. All right, so let's talk about radiation a little bit. The cause of radiation is always an unstable nucleus. All right, there are nuclei in nature which again, remember the nucleus. That is the center of the atom. It contains most of the mass. It holds the protons and neutrons. And when a nucleus is unstable, it will undergo radioactive decay. All right, and radioactive decay can take several forms. One, you can have one big nucleus and split into two smaller nuclei. So if you have an unstable nuclei, they have several ways of stabilizing. Right? So unstable going to from stable to unstable. First, if you have an unstable nuclei, one of the things that can happen is it can split. It can split into two stable nuclei, all right, of different atoms. It just falls apart into two different atoms. Another way is you got an unstable nucleus here, and it can just shoot off a little tiny piece of itself, just kind of like spit it out there. And you've got, so I meant to color that in, a little tiny piece of a nucleus. So it can eject a particle. The particle is shooting out there into the world. The last type of radioactive decay is that it can do to stabilize itself is it could be what is, okay, that's a little awful. It could be that what's destabilizing the nucleus is just a little extra energy. And what it has to expel, what it has to get rid of, is just that pure energy. It just has to shoot that lightning bolt out there, and then it's stable. So nuclei, unstable nuclei, have these three modes of stabilizing themselves. They can split, they can emit particles, or they could emit energy. All right? When you have an unstable nucleus emitting a particle, that type of radiation, it's like the universe's smallest little machine gun, because every single unstable nucleus is shooting off a particle, and there's moles and moles and moles, right? Trillions upon trillions of these atoms that are doing it all at the same time. So emitting particles are like, it's like the universe's smallest Uzi. When you have an unstable nucleus emitting energy, that's like a beam, like a laser beam. It's like the universe's smallest Death Star. So that these are the ways that radioactive decay. These are the modes of radioactive decay that occur in nature. And again, they all occur for the same reason. That is, you're starting with an unstable nucleus, and a nucleus. Every nucleus is committed to getting stable. It will do any one of these as long as their final resting state is a nice, round, stable nucleus. All right, and we'll hit all of these eventually. First, we have to do a little bit of review about isotopic nomenclature. You'll remember way back, so this is kind of us circling around towards the beginning of the semester. We talked about how you depict or write different isotopes. And you'll recall, isotopes are atoms of the same element that have different neutron counts. So the same element means you have the same proton count, but your neutron counts don't have to be the same for all. You can be oxygen, for example. You can be O18, you could be O16. Those are both oxygen because they both have the same number of protons, right? Oxygen will always have 8 protons, but O16 has 8 neutrons, O18 has 10 neutrons. And that's the difference between isotopes. So the way you specify what isotope you're talking about, the isotopic nomenclature, you can write it like this, or you can write another way to specify what isotope you're relating to is you do the elemental symbol with a dash and an A, or you can write out the name of the element with a dash and an A. And let's refresh ourselves with what these all these are. All right, so the L is simply the elemental symbol that you find on the periodic table. Z is the atomic number. All right, the atomic number is the number of protons in the nucleus, and then A is known as the mass number. And the mass number is the sum of the number of protons plus the number of neutrons in the nucleus. And just by way of refresher, the atomic number is on the periodic table. The mass number is not. All right, so you can look up the atomic number. You cannot look up on the periodic table the mass number. All right, that's extra information. All right, now the reason why I wanted to take a minute and review is because nuclear radiation is described using this nomenclature. So we need to remember what this nomenclature means. So, for example, if you had an element of carbon-12, all right, if you have an element of carbon-12, This right here tells you that you have 6 protons, and this 12 tells you that 12 is equal to the protons plus the neutrons. And because we have 6 protons in this nucleus, and again, we know that because of our mass number, sorry, not our mass number, our atomic number, we can find the number of neutrons in this molecule by subtracting the atomic number from the mass number. So carbon-12 has 6 protons and 6 neutrons. All right, now I want to take a moment and kind of introduce you to the types of nuclear radiation. That we see in nature. You're like, there's more than one type? Yes, 100%. All right, so first you have, the radiation, the symbols, and the composition. What is that radiation that we're talking about? All right, so we have the radiation, symbols used, and the composition, what that radiation is made of. And the first type that I'd like to talk about is alpha radiation. This is called alpha. Now the symbols used for alpha, these are called alpha particles. Alpha particles. The symbols are, you can use the Greek letter alpha. Now this is a particle, so it has a mass number and an atomic number. You're like, wait a minute. You're telling me we got 2 protons in this thing? That would be helium. Helium's an atom that has 2 protons in its nucleus, and that's another one of the symbols. Right? So you can, helium, another symbol that you'll see for an alpha particle is He plus, again with the mass number and atomic number. Another symbol that you'll see is just He2 plus. And that is because the composition of an alpha particle is a helium atom or I should say helium nucleus without electrons. Normally, a helium nucleus has 2 protons and 2 neutrons in it. A helium atom will have 2 electrons orbiting that nucleus. An alpha particle is just the nucleus without the electrons, and that's why you have a charge of positive 2. So an alpha particle is charged because it's the helium nucleus without the orbiting electrons. All right, that's alpha particles. There are beta particles. Oh, sorry, I used the Greek letter. All right, beta particles, and the symbols used here are, we use a Greek letter beta. It's kind of like a bee with a tail. And there are no neutrons in a beta particle. And wait, what? There's a -1 proton? What is up with that? What is a -1 proton? It's an electron. A beta particle is just an electron. And the way you denote that using isotopic nomenclature is a -1 for the atomic number. So the composition is just an electron. And that's all a beta particle is. Other ways you see beta particles symbolized, sometimes you'll see them with just a beta and a negative charge. You can also see them symbolized as an electron, 0 and -1, or just an electron. All of these mean the same thing. And so you'll see them all of them will be used. So beta particles are electrons, alpha particles, helium nuclei without the electrons. All right, let's talk about gamma radiation. These are sometimes called gamma particles or gamma rays. And a gamma ray, the symbol is the Greek letter gamma. And there are 0 neutrons in a gamma ray, and there are 0 protons. We've already seen an electron registers there as a -1. But what happens if there are no neutrons and no protons, right? What does that mean? Does that mean this thing has no mass? And the answer is yes. Right here, this means no protons, neutrons, or electrons. That means no mass. That's because gamma rays are pure energy. All right? What are they composed of? They're energy. They have no mass. They're not matter. So they're called gamma rays. I think I'm misspelling gamma. Let me check that. Yep. Sure am. All right. They're even spelled right in my notes. I'm that bad. I need that much help. Gamma rays. So these are called gamma rays. They're often called X rays as well. Same thing. They are pure energy. All right. So no mass at all. That's why they got double zeros. For both the mass number and atomic number. All right. This is where we part ways with the Greek alphabet. There are no delta rays or delta particles. You do have a type of radiation that you can come across is neutrons. And the symbol for a neutron is an N with a 1 and a 0. It's a 0 because there's no protons in a neutron. But it has a mass number of 1 because it turns out there is 1 neutron in a neutron, and the composition of a neutron is a neutron. So that should be pretty straightforward. The last type of radiation that we need to talk about is a positron. A positron. The symbol for a positron is a beta with a 0 and a 1. Sometimes, It could be written as a beta with a positive charge, or an E with a 0 and a 1, or an E with a positive charge. What the heck is that? You're like, that freaks me out because electrons have negative charges. Electrons do, but what is this? This is a positron. And what is a positron? It is an antimatter doppelganger. It is an antimatter doppelganger to the electron. It's exactly like an electron, except it's positive. And when it makes contact with an electron, they eliminate each other. They blink out of existence and are converted to pure energy. So it's antimatter. That stuff is real, if you can believe it. So those are the types of radiation that you will see, that we'll encounter as we work problems related to this chapter. But before we dive in a little deeper, we need to I need to revisit balancing. Balancing nuclear reactions. All right, now, the central idea behind balancing any chemical equation is the law of mass conservation, right? It's that matter cannot be created or destroyed, and so in the process of chemical change, you need to have balance. You need to make sure that the mass that you started with is equal to the mass that you ended with. And this is fairly straightforward for normal chemical reactions. For example, the decomposition of water, which is water turning into hydrogen gas and oxygen gas, right? This equation is unbalanced because even though we have two hydrogen atoms on the reactants and the product side, we only start with one oxygen atom, we end with two oxygen atoms, and we know that matter's not created or destroyed, right? So we need to make sure that we start with the same number that we're ending with. Now, we know how to do this. You multiply water by 2, so oxygen balances, and even though this throws hydrogen out of whack, you come back to the product side, multiply H2 by 2, and everything's good. You're balanced, all right? This is a little more, it's harder to look at. It's a bit more challenging when you're dealing with nuclear reactions, because the beautiful thing about a normal chemical equation is all your oxygens start as oxygens and they end as oxygens. But often in radioactive decay, the number of protons in your nucleus changes, and because the number of protons change, the identity of that nucleus changes with it, right? Because the identity of the nucleus is defined by the proton count. So, for example, consider this nuclear reaction where an isotope of radon-198 undergoes alpha decay. When it does, it becomes an isotope of polonium-194 after ejecting the alpha particle. Is this balanced? To the eyes that we've been carrying through this entire semester, You'd look at this and you'd want to say, no, it's not balanced, right? Because look, you start with one radon. Where's the radon? You don't start with polonium. Where did the polonium come from? And how do we deal with that alpha thing? Isn't that just helium? It can be confusing. It can be weird, right? Here's the deal, okay? Because the identity is shifting, which means that elemental symbols change, you can't balance in the conventional way, all right? Turns out this equation actually is balanced. Not a problem. This thing's 100% balanced. You don't have to add anything, change any numbers, whatever. The question is, how do you know? And when you're balancing nuclear reactions, you need to check two things. All right? You got to check first your mass number, then your atomic number. And when I say check, I mean your total. So, for example, because your atomic number tells you whether you have the same number of protons on both sides, and then the mass number tells you whether or not you have the same proton and neutron count on the same side. So for example, we have 86 protons on the reactant side. On the product side, we have 84 plus 2. The question is, are these equal? And the answer is yes. 84 plus 2 adds up to 86. That means our protons are balanced. Our mass number is 198 on the reactant side. On the product side, we have 194 plus 4. Do these add to the same thing? And the answer is yes and yes. And if both your atomic number and mass number add to the same thing on both sides of the equation, that means that you are balanced. That means that you're balanced. All right. So let's put this to work. Let's use this knowledge in a type of problem that you could face on the final exam. So determine the identity of the particle that balances the following reaction. All right, and the following reaction is the radioactive decay of nitrogen-17 into nitrogen-16. So the question is, what particle goes right here? What radioactive emission will balance this chemical equation? And if I may, really quickly, I just want to write up the identity of the radioactive particles. No, they're not radioactive particles. The radioactive emissions that we'll run into. So there's the alpha particle, the beta particle, the neutron, 1 and 0. Oops. The positron, which is a beta and a positive one down there, and then the gamma ray, which is 0 and 0. So these are the types of emissions that we have at our disposal. We need to figure out which one goes here. All right. Well, one thing's for sure. We know, even though we don't know the symbol, we can figure out what its atomic number is and its mass number is, because if our total atomic numbers need to be the same on both sides, there are 7 already on our reactant side. If this is going to be equal to our product side, then we already have 7, that means that we need to add 0. So there are no, whoops. Sorry, hang on one second. I started doing this in the wrong layer. Oops, sorry, hang on. There we go. So if we have 7 on the reactant side, 7 on the product side, that must mean the atomic number for whatever this particle is has to be 0, right? And because we know that, there we go. Because we know that, that means we can eliminate some, right? Because we need to have a 0 down there for the atomic number. So that means can't be alpha, can't be beta, can't be positron. All right, it's either going to be the neutron or the gamma. Now let's take a look at, so we first looked at our mass, or atomic number. Now let's take a look at our mass number. We have 17 on the reactant side. We have 16 on the product side. So to make this equal, that means that we have to have, whatever our emission is, it's got to have a mass number of 1. And turns out gamma's got a mass number of 0. So the neutron then is what goes right here in this box. The neutron. All right, let's do another example. All right, it's the exact same problem, just different nuclei. Determine the identity of the particle that balances the following reaction. Let's look at the decay of bromine 84 into potassium 84. All right, this one's a weird one, but don't let it scare you. We've got to figure out what particle is being emitted, just like we did last time. We're first going to look at our atomic numbers. It doesn't even matter which one you look at first. You can do mass numbers first. It's totally fine. All right, now look at this. We've got 35 on the reactant side. On the product side, we have 36. What's the only thing we could add to the product side to make this equal? Well, the only number that's going to do it is a negative 1. So we're looking for a particle with a negative 1 for its atomic number. And turns out that actually solves it for us right there. There's only one particle that has that, and that is the beta particle, or the electron. So our job is done here. We don't even have to look at the mass number. We already know it has to be 0, right? Because it's staying the same. This is a beta particle. Balances this reaction. Let's do one more. All right, exact same problem, but here we're looking at an isotope of samarium 148, decomposing into, I don't actually know what ND is off the top of my head, non-disclosure. They say you learn something new every day. I'm about to learn. Oh, neodymium. Neodymium, Keanu Reeves' favorite element. For the kids in the audience, because he played a character named Neo in a very old movie called The Matrix. Neodymium. If you want to see everything we thought, if you want to see 1999 in a snapshot, The Matrix has everything we thought was cool back then. It's in that movie. Go watch it if you haven't. And marvel how old and edgelordy we were right at the turn of the millennium. I guess we were millennials, or are. I am. Anyways, let's not get distracted. Okay, so what are we doing? We've got to find this particle. Let's start by looking at our atomic number. We start with an atomic number of 62. We end with 60 plus, there's got to be a 2 there for these to be equal. Look at that. There's only one thing with an atomic number of 2, one particle with an atomic number of 2. So this has to be alpha decay. This has to be an alpha particle. So actually that solves it for us right there. We don't even have to look at the other number, though we do know what it needs to be, and it needs to be a 4. All right. Okay, so that's not too shabby, right? For balancing nuclear reactions, you just have to look at the sum of the mass numbers on both sides of the reaction, the sum of the atomic numbers on both sides of the reaction. Make sure they line up. All right. Let's shift gears a little bit and talk about, there it is. Nuclear reaction types. Nuclear reaction types. The first type is something called alpha decay. Sometimes it's called or alpha emission. So alpha decay or emission is when you have an element, again, right, an unstable element with a mass number A and an atomic number Z, And it is going to spit out, it's going to machine gun out an alpha particle. I'm going to call this element 1. And it's going to become, actually, that's going to get confusing. I'm going to call this X rather than EL. And the product is going to be Y plus an alpha particle. And the thing is, the mass number for Y is going to be A minus 4, and the atomic number for Y is going to be Z minus 2, because it lost that mass and those protons when it ejected the alpha particle. So it's going to change identity, and its mass number will decrease by 4, its atomic number will decrease by 2. That's what happens during alpha decay. During beta decay, or this is also called beta emission, during beta emission, we're starting with an isotope, X, and it is emitting an electron, all right? Now, here's the thing. It is the nucleus emitting an electron. It's not losing an electron from its electron cloud. The nucleus is shooting an electron out into the void, and an electron is a beta particle. And during beta decay, your mass number stays the same, but your atomic number increases by 1. And the reason why it increases by 1 is because it's ejected an electron, and for your total atomic numbers to balance, if you've got that negative 1 floating over there, you need a positive 1 here. What is literally happening inside the nucleus is you have a neutron within the nucleus splitting into a proton protons are 1 and 1 plus an electron, which is 0 and negative 1. So that's what's going on within the nucleus, and that's why these add up. You have a neutron turning into a proton. That's why A stays the same, but that's why your atomic number increases by 1. For gamma, gamma emissions, you gotta watch out for gamma emissions because you start out with a nucleus and the nucleus does not change because you don't lose any mass. You don't lose protons or neutrons when you emit a gamma ray, because gamma rays are pure energy that doesn't change the mass. So you actually have the exact same nucleus composition before and after. It's what made it unstable is this nucleus had absorbed energy, it releases it, and that stabilizes it. So gamma emission can be a little bit of a tricky one because of these double zeros. We have 3 more types of nuclear reactions to look at. The next one is called positron emission. That's when the nucleus spits out a positron. So you start with a nucleus X, and it is going to eject a positron which means its mass number stays the same, but its atomic number decreases by 1, and that's because we've spit out that positron, so this is going to go down. It'll have a different identity than the nucleus we started with. Now, the next two are not emissions. They're actually the nucleus eating something to get bigger. And one is called electron capture. And it is exactly what it sounds like. It is when a nucleus, oops, sorry, I didn't mean to do a chi, reacts with an electron. And it's, again, it's not that the electron starts orbiting the nucleus eats it, absorbs it, and it becomes a different nucleus. It changes the identity of the nucleus because now it has Z minus 1 protons. What happens in this reaction is literally a proton and an electron fusing to become a neutron within the nucleus of the atom. It's really weird, but super cool. The last type, the sixth type is something called neutron capture. And it is exactly what it sounds like as well. You've got a nucleus A that is eating, absorbing a neutron, and it'll have the same identity because Z doesn't change, but the mass number does change. It grows by 1. So these are the 6 types of nuclear reactions that we run into, and yeah, let's put them to the test. Let's do a few examples. Oops. All right. So, write a balanced chemical equation for the following reactions. All right, and the first is going to be positron. Oh, here, hang on. I just want to trot out the periodic table here. Positron emission of carbon-14. All right, so here, and this is the reason why I brought out the periodic table, this is another balancing type of problem, and we start with carbon-14, and actually, I also want to bust out, whoa, there we go, my particles, because this is going to be helpful. So we've got a reaction going for C14 where it is undergoing a positron emission. Now, the first thing that we want to do with carbon is located on the periodic table, right? And so that tells us, even though the problem didn't explicitly tell us that We had 6 protons. We know because carbon is the 6th element on the periodic table. Now, we don't know what nucleus this is going to become, but we can figure it out because we were told that this is a positron emission. And so the positron particle has 0 for the mass number and 1 for the atomic number, all right? And so we know that we have 6, our atomic number is 6 on the reactant side. On the product side, we have 1, an atomic number of 1. So we need to add 5 for this to balance out, right? And so we know that whatever this nucleus is, it has an atomic number of 5. Now we have to figure out the mass number, all right? And again, just like we did last time. Whoops. Let's make that green. There we go. We know we have 14 on the reactant side, and this equals, let's see, we've got 0 so far on the product side. That means that the mass number here must be 14 if these two are going to be equal. You're like, okay, Josh, that's great. I could figure out the mass number. I could figure out the atomic number. How do I know what symbol? Should I just put a C because it's carbon? And the answer is no, because it's not carbon. You need to look at that mass number and find the nucleus on the periodic table with that mass number, in this case boron, and boron then is the nucleus that belongs on the product side, all right? This is honestly one of the more tricky things. It's tricky to remember because, again, the identity of the nucleus is based on the number of protons, and we're not used to elemental symbols changing. This is the one type of reaction where that happens. So just be aware, your elemental symbol will change if your atomic number changes. If your atomic number doesn't change, the elemental symbol remains the same. All right, let's do another example. Again, same problem, but let's do the beta decay Let's look at the beta decay of iodine 122. That is a gigantic isotope. All right, so we have iodine 122. And again, you got to find iodine on the periodic table. Its atomic number is 53. So we put a little 53 there. And it is undergoing beta decay. It's going to turn into something. We haven't determined what yet. But we know it's going to emit a beta particle. All right, and so beta particles have a mass number of 0 and an atomic number of -1. All right, so now we can find the atomic number for our nuclei because we have a 53 on the reactant side. And we know that it has to equal the atomic number on the product side. Right now we have a -1. That means we've got to have an atomic number of 54. Now let's figure out the mass number. We have 122 on the product side. Sorry, on the reactant side. On the product side, we have a 0, which means we also need a 122 for the mass number. Now we can find the elemental symbol based on the atomic number. We got to find the atomic number 54, which is right there. It's xenon. And so there it is. That's the balanced chemical equation. The identity of the nucleus is xenon. Let's do two more examples, and then we'll close out. All right. Oops. So we have let's do iron 55 undergoes electron capture. All right, now here we have iron 55 capturing an electron, which you'll remember is a beta particle. So we've got to figure out what this is going to turn into. All right, now we need to know our mass number of iron. This is going to work out. So iron is right here. Our mass number is 26. So we have 26 minus 1 equals, well, 26 minus 1 is 25. Right? For the mass number, 55 plus 0 is 55. So now we just got to find what element has an atomic number of 25. Manganese is our answer. So manganese, which is Mn55, balances the electron capture that iron 55 undergoes. All right, last example for the semester. Let's look at the alpha decay. Of polonium-212. All right, the alpha decay of polonium-212. Now, starting with polonium-212, and we don't know what it's turning into, but we do know that we're shooting off an alpha particle. All right, that means, well, let's see here. We got to figure out our atomic number for polonium. It's right here. It is 84. So we have 84 is equal to something plus 2. That's got to be 82. And then 212 has to be equal to something plus 4. Well, that's got to be 208. Now, the identity of this nucleus is determined, as always, by the atomic number, which means that we have an isotope of lead on our hands, Pb. All right, and that is the business. That is, that's how you do these. So what you've seen today is what you're going to see on the final exam. That's how this is going to show up. Now, like, I mean, you know me, I can write some tricky problems. I can really try to push you to think, push the edge of the envelope in the testing scenario. I am not going to do that with these problems. Again, all of this stuff is brand new today, which means I'm going to be as straightforward as I possibly can. How you'll see these formatted is, and again, I haven't decided the total number of problems. All that stuff is still up in the air. But let's talk for a minute about how this is going to manifest on the final exam. So let's talk about radiation in the final. All right. So so problem types. I could give you X going into Y and ask you to identify this, right? Just like we started out with. Identify. I could give you a reaction. So we've got X going into Y plus alpha. And so I could first, I could ask you to identify the particle. Here, I'd be asking you something slightly different. I'd ask you to identify the type of nuclear reaction. And so like this would be example alpha decay or alpha emission, right? There's only 6 of these. There's alpha decay, beta decay, gamma emission, positron emission, neutron capture, electron capture. You don't have to memorize them. You can write them on your equation sheet. And third and finally, I could give you the nucleus plus the nuclear reaction type right, so tell you positron emission, neutron capture, and I could ask you to identify the nucleus that balances the reaction. All right, and that's the exact type of, that's the example that we're doing right here at the end. So those are the 3 types of questions that I could ask. I might focus on one. Realistically, I'm probably going to ask all 3 at least once. So there's going to be a mix. But that's how this is going to show up on the final. So what I would recommend is on your exam sheet, I wouldn't leave home without 1, the reaction types, I would have all of those written out, and 2, the particles. You saw how I had those as a reference for each of the problems. I would have those written on there as well, so you have that for a reference to help you as you move along. All right, so that does it for lecture today. We're a few minutes early. Again, I'm going to be holding office hours in lab tonight, so drop by if you have any questions, and I will catch you on Thursday.